Hey geometry students, I decided to make some videos for you this week. I thought that would be better than trying to leave you text stuff that you have to read and work through. So what I'm going to do is I've made these videos so that you can follow along. I would like you to take notes just as if I was writing on the board, and we'll just try to do class as usual as we possibly can. So on that note, there's a couple things that I wanted to remind you about with homework. I just graded a bunch of homework for your classmates, and I'm sorry I can't be there today to pass back all of the homework that I've graded for you. But as I was grading it, I noticed that there was some things that we started out doing really well that we're not doing so well anymore. Like, for instance, giving solutions instead of just answers. I know that we're working on logic stuff. And so a lot of times there's like yes or no answers for questions. You still need to explain your reasoning. Regardless of what the question is asking, a one-word answer is never appropriate. So please remember that homework solutions are demonstrations of how to obtain the answer, not just the answer. Second thing is we're writing properties of congruence and properties of equality without using the words congruence or equality. So for instance, if I'm writing a proof and I want to write why A equals B implies that B equals A, well, that's not just the symmetric property. And it's definitely not just symmetric. So that is not an appropriate answer. You need to write the symmetric property of equality. Okay, mostly for your homework it's okay if you abbreviate and stuff too. So prop of EQ is all right. I know what that means. If AB is congruent to, let's just say AB is congruent to AB, that is the reflexive property of congruence. Okay, I'm seeing a lot of stuff that just says reflexive. But we need to be a little bit more precise. So there's that. The next thing is I'm also seeing a lot of answers that depend on diagrams where I don't see diagrams in your homework. So please remember, copy all diagrams. If I say you to draw something or sketch it or construct it, whatever the instructions are. If there are several questions that rely on a particular diagram, you should have that diagram in your notebook or in your homework. I have a degree in mathematics, and I cannot do your homework problems without at least copying the diagram down. So it makes you curious as to how you're getting solutions without doing the same thing. And then lastly, remember, I give you a lot of odd questions intentionally so that you can check your work. So please go back, check your answers. That is not optional, that is mandatory. You should be checking your answers as you're working so that as you're working, you're getting instant feedback about whether or not your answers are correct. So here's what we're going to do today. The first thing we're going to do is go over your homework assignment. The Chapter 3 introduction. The next thing we're going to do is talk about properties of parallel and perpendicular lines. Remind ourselves of some things from algebra that we've already talked about in the last week or so. And then the last things are going to introduce some postulates from Section 3.1 and Section 3.2 that we're going to apply when we talk about lines. So first thing, homework. So the first three problems were to find the slope of the line that passes through the 2 points. All you need to do is use the slope formula, m equals y2 minus y1 over x2 minus x1. If you don't have this formula on a note card, put it there. You need it to be there. The correct answers are, let's see, let's just do them. The first one was -6 minus 2 over, let's see, 3 plus 1. -6 minus 2, that's -8. 3 plus 1 is 4. So that turns into a -2. For the second one, the slope was 3/2. So the correct answer for number 2 is 3/2. And the correct answer for number 3 is a -3 minus 1. It is a +4. All right, and then for numbers 5, 6, 7, 8, 9, and 10, I asked you to find the slope of the line that has the following angle from horizontal. I gave you also the tangent formula, reminded you of the tangent function. So we're going to use m equals tangent theta, where theta is the angle from horizontal, and m is the slope of the line. Okay, so for these should be pretty easy. All you have to do is plug them into your calculator. The tangent of 45, we actually did in class, that's 1. The tangent of 145 is, let me get my calculator out. -0.7. And I said 3 decimal places, so, well, it's actually 0.700, so we can just leave it at that. Remember, degrees from horizontal means that the line makes a 145-degree angle from the right side, so from like the easterly direction, or the positive x direction, with a horizontal line. Okay, so it makes sense that this slope is negative. The next one is tangent of 110. That is negative 2.74. Tangent of 72 is about 3.078. And then the last two we talked about in class 2, tangent of 90. That's asking for the slope of a line that's perpendicular to a horizontal line. So perpendicular to horizontal means vertical. What's the slope of a vertical line? It's undefined. You're going to get an error when you type that into your calculator. And then lastly, tangent of 180 is 0. Okay, if you got completely different answers typing the same thing in, it means your calculator's probably on radian mode. So remember in class we switched our calculators to degree mode. Here's my calculator. If I push the mode button right here, okay, there's the options between radian and degree. You need to select degree because we're measuring our angles in degrees. Then let's see, for 11 through 16, numbers 11 through 16. Remember, for my positive slopes, I'm going to do the angle is equal to the tangent inverse m, and then for my negative slopes, I'm going to do theta equals tangent inverse of m plus 180. All right. Okay, so if m is equal to 2, let's collect my positive slopes over here. I'll collect my negative slopes over here. That way I don't have to worry about going back and forth between formulas. Number 11, we have m equals 2. Number 12, we have m equals 3/2. Let's see, number 15, m equals 0. I already know that let's see, theta is going to also equal 0 for that one. Then negative slopes are negative square root of 3, negative 1. Let's see, if the slope's negative 1, that's 135 degrees. And 15, 0 again. If the slope is 0, what? Oh, sorry, 16. That's negative 1 over the square root of 3. So let's get rid of that. M equals negative 1 over the square root of 3. All right, so let's plug these in. So for m greater than 0, I'm going to use the formula tangent inverse. There's tan. Remember, tangent inverse is the button as what I get when I push the second button before I push tangent. You can see it right there. So tangent inverse of 2, 63.435, let's say. Tangent inverse of 3/2 is 56.309, let's say 0.310. That makes sense. That should be a pretty a positive slope that's just a little better than 45 degrees, because rise over run says I go over over 2 up 3. And then lastly, that's a horizontal line. It's horizontal line, angle 0. It is 0 degrees from horizontal. It is already horizontal. And then if m is less than 0, our formula was theta equals tangent inverse of m plus 180. So I'm going to do tangent inverse of negative square root of 3 plus 180. That's 120 degrees. Negative 1, that's 45 degrees from 90, so I can figure that out in my head, but let's just go ahead and do it anyway. There we go, 135. And then lastly, negative 1 over the square root of 3 plus 180 is 150 degrees. All right. Then 17, give the equation of the line that has a 45-degree angle from the horizontal and a y-intercept of 3. So here's the point 0, 3, and it makes a 45-degree angle. This is the line y equals x plus 3. Okay, we would use tangent tan theta. If theta equals 45, tan theta is 1, so our slope's 1. Number 18. Give the equation of a line that is 115 degrees from horizontal and has a y-intercept of negative 8. Okay, y-intercept of negative 8. I need to find the slope first. I have the angle from horizontal, so I'm going to use my formula, m equals tan theta, where theta is that angle from horizontal. That's tangent of 115, which is negative 2.145. And since I've already given you the y-intercept, you should know that if my equation is y equals mx plus b, then m is negative 2.145, which I just discovered. Sorry, you can't see that. Then I've got my x plus negative 8. So let's write that all together as y equals negative 2.145 x minus 8. Okay. Now, on to the good stuff. All right, let's look at number 9. It's going to lead us right into our discussion for the content of today's lesson. So it says, consider a line S with equation y equals root 3 times x, and a line T with equation y equals x. So I'm going to sketch a graph of both of those lines. Okay, here's y equals root 3, so that's the line S. So there's y equals root 3 of x, or times x, excuse me. And then the other one was just y equals x. So that's a 45-degree angle, a diagonal line. And they both pass through the origin. Y equals x is this one. Okay, so part A says use your calculator to graph both lines. You should get something to look like this. I had some students that got some weird stuff because they put in that's not the same function as y equals root 3 times x. This function starts at the origin and goes like this. This function starts at the origin and is a line. Okay, so what I ask you to do next. Label the angle between the horizontal axis and line S as angle C. So here is angle C. Then use the slope of the line to find the measure of angle C. Okay, so the measure of angle C then is the tangent inverse of the slope, which is the square root of 3. And tangent inverse of the square root of 3 is 60. So this is a 60-degree angle, angle C. Then part C, label the angle between the horizontal axis and line T as B. So here is angle B. Sorry, I just lost my lights. Okay, and then do the same thing. Use the formula that we've been using to find the angle. The measure of angle B is tangent inverse of the slope, which is 1. We already know that's 45 degrees. Okay, and then lastly, part C, label the angle between lines S and T as angle B. Or no, excuse me, angle A. So here's angle A. All right, then what? Using the angle addition postulate, write a statement that relates the measures of angle A and B to the measure of angle C. You can see here from the drawing, from this diagram, that angle A and angle B are adjacent angles, and that C is the angle that's made up of both of them. So by the angle addition postulate, we have that the measure of angle A plus the measure of angle B is equal to the measure of angle C. That's just a statement of the angle addition postulate. So then I know the measure of angle C and I know the measure of angle B. Using the subtraction property of equality, I can say that the measure of angle A is the measure of angle C minus the measure of angle B. And so then the measure of angle A is 60 minus 45, which is 15. Okay, notice that for this formula for lines with positive slopes, we came up with theta, the angle between the two lines, is the tangent of the larger slope, I'll call that m max, minus the tangent of the smaller slope, I'll call that m min. So now we have a method to find the angle between two lines. That's pretty interesting when their slopes are both positive. We'll maybe work later on a formula that gives us the angle between two lines when the slopes are negative. But I don't want to worry about that right now. So let's talk about parallel and perpendicular lines. I'd like to review what we know about those from algebra. So our first goal is going to be to describe parallel and perpendicular lines and review what we know about them from algebra. So let's start with parallel lines. Okay, what are parallel lines? Parallel lines, usually, I've already taught this lesson today, actually, the day I'm making this video, and I asked my class, what are parallel lines? Everybody says that they're lines that do not intersect. Okay. All right, so that's what I get. Some other things that I usually get are lines that have the same slope. Which is good, because that's how we describe parallel lines in the context of algebra. So for y equals, let's say, well, let's do y equals mx plus b. We'll call it b1. So if I have a line y equals mx plus b1, then a parallel line is any line that has the same slope, even though it can have a different intercept. So really, since the slopes are the same, those lines don't intersect anywhere. Okay, but Euclid didn't have equations to describe lines. Okay, remember Euclid was doing what we call synthetic geometry. This is analytic geometry. So here's the analytic picture. Let's look at the synthetic picture. The picture from synthetic geometry, remember, that uses constructions. So Euclid realized that if you had a line and a point, it was always possible to construct a parallel line. But he couldn't prove why that was the case. And so he made a postulate, which is the parallel postulate. Okay, so what the parallel postulate says is that for any line and any point not on the line, there exists a second line that's parallel to the first, or there exists a second line that doesn't intersect the first. It's not immediately clear why there should be a second line that doesn't intersect the first. You know, how do we know that there is a line that doesn't intersect it? What if every other line intersects it? Well, Euclid made that postulate, so in Euclid's system of geometry, it does always exist. Now we can show that using analytic geometry, just the properties of coordinate spaces imply that parallel lines exist. And we're going to show that right now. So let's copy this down first. The parallel postulate says that for any line and point not on the line, there exists a line parallel to the first that passes through, getting ahead of myself, through the point. Okay, so here's what we're going to do. First thing we're going to do is prove that this is true using analytic geometry, and then I'm going to show you a method on how to find the line, given a line and a point. So first, let's use analytic geometry to prove that the parallel postulate is true, that we don't need it as a postulate, that we can prove it. Prove it's a theorem of analytic geometry. Sorry, I just got a text, got a little distracted. All right, so intersections. Let's consider the system of equations for two lines, y equals mx plus b1 and y equals mx plus b2. Okay, so this is a system of equations, which means it describes two lines. And in this case, I'm gonna write that b1 is not equal to b2. So here we have two equations, each of a different line because they have the same slope but different y-intercepts. So remember last class we talked about two lines having the same equation when they have the same slope and same y-intercept. So since these y-intercepts are different, these are different lines. So the question is, do these lines intersect? Or can we come up with two lines that don't intersect? We're going to see in a second that these two lines don't intersect. So, according to the subtraction property of equality, since y equals mx plus b1 and y equals mx plus b2, let's just say since these two quantities are equal, I can subtract each of them from one side of the first equation. Okay, the subtraction property of equality says that I can always subtract equal amounts from each side of an equal sign. So I'm going to start with my first equation, y equals mx plus b1, and I'm going to subtract these equal amounts from each side of this equation. So I get y minus y, and I get minus mx plus b2 on this side. Okay, y minus y is 0. On the right side, mx plus b1 minus this quantity. Let's just distribute the minus sign so we don't have any questions about it. Then we get mx minus mx, those go away, and then we just get 0 equals b1 minus b2. Or if I add b2 to both sides, I get b2 equals b1. But this is a contradiction. Remember, a contradiction is an equation that is never true. It's never true because I've said that b1 and b2 are different numbers. So for example, let's say b1 is 2 and b2 is 3. Well, if I start with 2 and 3 here, then what I get down here is 3 is equal to 2, which is never true, right? So so what do we do when we're solving a system of equations and we get a contradiction at the end? If you remember from Algebra 2, that means that there is no solution. Now this is going to make a lot of sense for our current topic when we really think about what the solution of a system of equations is. The solution of a system of equations, remember, is a single point xy that satisfies both equations. Okay, and last class we talked about that satisfying the equation meant it was on the line. So satisfying both equations means on both lines. On both lines is how we defined the intersection. So basically, since this system has no solution, these two lines have no intersection. And so therefore, we can find two lines such that the lines don't intersect. In fact, for any line with a slope m, as long as we have another line with a slope m, the y-intercept doesn't even matter. The y-intercept doesn't even matter as long as it's not the same as the first one. As long as it's not the same as the first one, we've got a parallel line. So what does that look like? Well, here's a coordinate system really quickly. Here's a line. Suppose this line has the same slope, but a different intercept. This line, same slope, different intercept, etc. So all these lines have the same slope, but they have different intercepts. Also, something interesting to note is, remember, our formula for angle only depended on slope. Right? It only depended on the slope. It didn't depend on the y-intercept. So all of these lines also make the same angle with the horizontal, which you can see here, and here, and here, and here, and here. All those angles are the same. That's going to come in handy, or it's going to be really important later. So now that we've established that the parallel postulate is true, that indeed there is a parallel line for any other line, let's demonstrate with an example. So suppose we have y equals 2x plus 1, my favorite line, and suppose this is the point 2, 7. I wanted 7 too, but that's okay. We'll just do 2, 7. So let's find the parallel line to this line. Well, we just discovered that the parallel line to this line is any line that has the same slope. So if our line y equals mx plus b is parallel, then m is equal to 2, because it has to have the same slope in order to be parallel. So what I'm going to do is I'm going to replace m with 2, And now I have a line that has a slope that I don't know the intercept of. But last class we already talked about finding the intercept of a line if we knew the point, a point that the line was on. And that was by plugging in the coordinates of the point, x equals 2 and y equals 7 in this case. Because the equation has to describe the relationship between 2 and 7, it also has to describe, or excuse me, it has to be true when we plug it in. So we can ask ourselves, 7 is 2 times 2 plus what? So I imagine we're going to get b equals 3. But let's plug these in just to be sure. So we get the y is 7, the x is 2, and there's our plus b. So 7 equals 4 plus b. Using subtraction property of equality, let's subtract 4 from both sides, and we get 3 equals b. So my final answer for this question is y equals 2 times x plus 3. So given an equation and a point, my process for finding the line is first to find the slope. Okay, my process for finding the parallel line, I should say. I want to find the slope. In this case, it's the same. And step 2, I want to find the intercept using the same method as before. Okay, I'm running out of time here, so that's why I'm trying to move so fast. Nice thing about videos is you can always pause, keep writing, rewind, look at something again, or even go back later. I don't know, if this works out really well, I might try to incorporate videos into our class discussions more. So that was the parallel postulate. Next, I want to talk about the perpendicular postulate. So let's talk about perpendicular lines. Perpendicular lines, we remember from algebra, are lines that have opposite reciprocal slopes. And already this year in geometry, we've defined perpendicular lines as lines that meet at 90-degree angles. Okay, so I'm going to kind of do the same thing I did last time. And maybe we'll do a couple different examples. I'll start off with the same kind of thing. So suppose I have a point and a line. The question is, does there exist a perpendicular line that goes through that point? Well, it seems that I can draw one, so I expect that there is one. Again, Euclid cannot come up with no reason why that should be true, so he made a postulate called the perpendicular postulate. I guess this isn't an example. I turned it into our description of the perpendicular postulate. The perpendicular postulate says that for any line and point not on the line, there exists exactly one perpendicular line that passes through the point. Okay, this one's actually a little easier to construct. I don't think that I'm going to do the construction today because this video is getting long, but we'll do the construction when I get back. Okay, I'll talk about an extra credit. Question 2. which actually might help you figure out how to do the construction in the first place. So that was Euclid's perpendicular postulate. Let's go ahead and demonstrate that his perpendicular postulate is true by solving that particular problem. So suppose we have a line and a point. Let's say our line, I'm going to tilt it a little bit. Let's say our line is y equals 1/2 x minus 1. And our point is, I don't know, 3, -1. Okay, our goal then is to find the perpendicular line that passes through the point. Find the perpendicular line that passes through the point. All right, so again, for every line, we're going to need to find the slope and find the intercept. Okay, so you should notice that that's kind of a theme. Let me turn that light back on. Okay, so first thing we're going to do is find the slope of the line that we're looking for. The slope of the line that we're looking for, if this slope is 1/2, the slope that we're looking for, which I'm going to call m with a little perpendicular sign, is -2. And if the slope is -2, then the equation is y equals -2x plus b. And if the equation is y equals -2x plus b, then that describes the relationship between 3 and -1. So -2 times 3 plus b is -1. So let's plug those in. -1 equals -2 times 3 plus b. That implies that -1 equals, I'm going to put a little implies symbol there. Then -1 equals -6 plus b, so it looks like b is equal to 5. So my perpendicular line, which meets at a right angle, is the line y equals -2x plus 5. All right, and let's go ahead and just plug these two lines into our calculator to be sure. So they were y equals -2x plus 5 and y equals 1/2 x minus 1. I'm going to push my y equals button. So my first line is y equals 1/2 x plus, or rather -1, excuse me, -1. And the second line is -2x plus 5. So if I graph those two lines, there's 1/2 x minus 1, there's -2x plus 5, and I should see that this goes through the point 3, -1. So I'm going to go to my stat plot to plot that point so that you can see. Okay, it's already, wait, was that on? Yep. Three, -1, graph. There's 3, -1 right there. That little point. Red line's going to cut right through it. Okay. All right. So there are some theorems that I want you to take a look at. Theorems 1, 2, and 3. They are pretty straightforward. So I'm going to leave the proofs for you. Okay. I'll just give a brief statement of each of them. The first is that if two angles in a linear pair are congruent, then they're right angles. So if this angle is congruent to this angle, for instance, then they're right angles. Why is that important? Well, if that's a right angle, then those two lines are perpendicular. So that's theorem 3.1. Excuse me, theorem 3.2. If two adjacent angles have perpendicular sides, then they are complementary. Remember, adjacent angles are angles that share one side and then don't share any interior points. So this angle here and this angle here are adjacent angles. So if the adjacent angles are complementary, if this angle 1 and this is angle 2, that means measure of angle 1 plus measure of angle 2 is equal to 90. Well, then this angle on the outside, by the angle addition postulate, has a measure of 90 degrees. So this is a right angle. So that means that their non-adjacent sides are perpendicular. 3.3, if two lines are perpendicular, then they meet to form four right angles. Basically, we define this sort of situation to be perpendicular lines. However, what this theorem says is that if that's the case, then these three angles are also perpendicular. So another way you could state that theorem is that in a perpendicular intersection, all four angles are congruent and all four angles are right. Okay, last thing, very last thing, I promise. This video's getting long. We weren't very careful when we defined perpendicular lines. Okay, the definition we gave was perfectly fine for plane geometry. So that's geometry that takes place only in a single plane, like the Cartesian plane. However, if we think of geometry in space, where we have coordinates in 3 dimensions, or just if we think of it including 3-dimensional objects, then we have to be a little more careful about how we define parallel lines. Because as you can see from this drawing of a cube, I can highlight two lines in this cube that don't intersect in 3D space and yet are not perpendicular. So this line that passes through the top segment of the front face, and let's say this line, I'm going to use a different color because I can. This line that passes through the back segment of the right face, although we see their intersection, or we see an intersection of the red and blue lines on this paper right here, these lines actually don't intersect in that space. Those lines don't intersect if we think of a 3D cube. If we think of a 3D cube, they don't intersect. But they're not parallel. They're definitely not parallel. So we need to be more careful. We call these lines skew lines. Skew lines are lines that are not parallel but also don't intersect. So skew lines, let's just, for skew lines you just need to be able to identify them. You just need to be able to identify them. Okay, so for your homework this evening, you have a handout. Okay, the title of the handout is handout 3132. Let me check on that just to be sure. Yeah, it's called homework 3.1 and 3.2. At the top, there's some textbook questions for you to do, and there's some additional examples. Okay, the textbook questions are mostly just identifying stuff, and the examples you'll work through a little bit, find some equations for some lines. All right, thank you for watching. I appreciate your patience and your attention. Have a good night, and I will see you, and I'm just kidding, I won't because I'm not there, but you will see a video of me next class.